Okay, so we learned about improper integrals that are fairly obvious, ones that are integrals over an unbounded interval, for instance, from 1 to infinity. Now we're going to learn about something slightly more subtle type of improper integral. You can see this one right here could be mistaken for a well-defined Riemann integral. That is one that could be evaluated by using Riemann sums. However, if we think a little bit more about the integrand here, what this function is doing, then we actually see that there is an infinite discontinuity at 0 for this function, right? This graph would look something like this. This would be our y equals 1 over square root of x. And if we integrate from 1 all the way over to 0 here, looking for the total area under the curve, then you can see we've got another one of these regions that we're asking for the area of, which is infinite, right? Dot, dot, dot here. And so we need to evaluate it according to our definition, which is to say we want to actually just look at a t value here and then let t approach 0 so that we're actually just looking at the area here, which is a well-defined Riemann integral. So you can see here I have our definition for how I would evaluate this infinite discontinuity right here, this integral over the infinite discontinuity. It's an integral between just two fixed real numbers, a and b, but at the one end, let's see, at the left-hand end, the a here is 0 in this case, and that's where there's an infinite discontinuity. So we have to know what the integrand looks like to be able to write the appropriate limit to evaluate this integral. So you can see the idea is the same as before. You have to replace sort of the problematic bound of integration with a t, and then let the t approach the desired position. Okay, and so in this case, t is approaching 0. Right, so as you can see, we're approaching 0 from the right. So this is going to be a little bit more tricky to discover when an integral is actually an improper integral. So you're going to have to think about the integrand and what's going on with the graph of that function between the limits of integration. Just like before, we have the same pieces of terminology, that it's convergent when the limit is finite and that it's divergent when the limit is infinite. And in the same way that if we have sort of a two-ended problem with integrals over an infinite unbounded interval, we can have sort of a two problems, two infinite discontinuities to worry about at once in an integral. So for instance, say we wanted to evaluate something like integral from -1 to 1 of 1 over the cube root of x. Well, notice that the cube root of x has actually got an infinite discontinuity in the middle, right at 0. And so we would have to break this up into two different improper integrals, each one with just a sort of single infinite discontinuity to worry about. So we would break this up into an integral from -1 to 0 on the one hand, and an integral from 0 to -1 on the other. And again, I have to choose 0 here because that's where an infinite discontinuity is for this function, 1 over cube root of x. And so each one of these integrals needs to get evaluated according to a limit, right? So in the first integral, the problematic point is at 0, so I'm going to have to take a limit there. and t will have to approach 0 from the left for this integral. Now there's also the second integral here, and the problematic point for this one is this lower limit of integration. So I'm going to need to have another bound, another variable approach the bound that we want there. So again, I'll use an s because it is a totally different integral from the first one. And we have s approaches 0 from the right this time. S will be a positive number getting closer to 0. Okay. The graph for this situation would be fairly obvious. You would have our asymptote, our infinite discontinuity, right? And then here would be, say, 1 and minus 1 for this function. And we'd be after, yes, the whole area here and here all at once. However, the way that we're actually evaluating it, according to my definition right here, is to take here a t and let it go to 0, and take here an s and let it go to 0. And so we're actually just taking two different limits for these two different sides. Both of those t and the s will be closing in on 0 there. Okay, so remember, this is the way you're going to have to evaluate integrals when the integral is over an infinite discontinuity.